the surfactant which is present within the oil drop. Now the oil drop as shown here, it's not exactly of this shape, it can be any shape. Now, I've shown you a cross section of the oil drop. Now it can be of any particular shape. Usually these shapes are oblong. What that means is the shape will be tapering at the edges and it will be thicker at the center. Now what happens is, due to this particular geometry, the surfactant is present over this particular area, that is towards the center of the drop where the height of the drop is more. Alright. Now what happens is, at this particular instant, the detergent molecules will be concentrated, and over this particular part the detergent molecules will be less concentrated, or their concentration will be less. Now what that means is, the molecules over here have reduced the surface tension by a lesser amount than the molecules that have reduced their surface tension here. This means that now the surface tension which is being reduced here causes the oil drop to shrink in size, because as the surface tension reduces, the oil drop tends to spread itself. The sigma diagram that we had seen earlier, the value of sigma reduces over the surface. The surface tends to reform itself or regain its original state, which is that of the planar surface. Looking at it in a little more detail, the center of the oil drop has greater concentration of surfactant than the tapering ends. Now again, these ends are tapering, not oblong as shown here. So what happens is, there is an unequal distribution or unequal surface tension distribution. This unequal surface tension causes the oil drop to reduce in this particular direction, and then causes it to expand. Now what happens during this particular expansion is, the surfactant molecules which is present towards the end, they tend to recirculate, or they tend to cause a recirculation over this small area enclosing the oil drop and the surface of the liquid. The green line indicates the surface of the liquid. Now when this recirculation happens, there is a shear force which acts, which I'll be talking about in the next slide, which causes the expansion of the oil drop. Now here we are again back to the oil drop, where concentration of the detergent molecules is greater at the center because it has greater volume over here, and it is less at the end because we have a tapering over here. Now let us assume two independent surfaces, that is the upper surface where the concentration is more, that is just below the center of the oil drop, and towards the end. Now what happens when we have this particular phenomena is that there is a shear force which acts. I'll be explaining how the shear acts. What happens is, this particular reduction in surface tension is more than the reduction in surface tension at the ends. Now the surface tends to move outwards. The surface at the end tends to move outwards, but in a very low speed, or at a very low speed, and the surfactant molecules tend to accumulate themselves over the surface of the water. Now, realizing all of that, we consider two or three velocities in this particular case. V2, that is the velocity of the top layer of the surfactant, that is surfactant over here, and the velocity at the bottom layer of the surfactant, that is velocities over here, as V1 dash, V1 dash and V. Drawing this velocity diagram, we can see that there is a variation between V2 and V1 dash, where V2, that is this particular velocity, outward velocity, is greater than this inward velocity or the V1 velocity, and this V2 velocity, again comparing it with the other end velocity, is greater than this particular velocity. Now this causes a condition of circulation. Again, as I mentioned, I'll stick to my promise and will not go into the mathematical derivation of this, but it creates a condition of circulation across this particular membrane or this particular layer. And this small area across the surface, due to this condition of circulation, causes a shear force. This shear force causes the liquid to move with respect to each other or relative to each other, and causes the oil drop to expand. Now, let us get down to the most important process of our oil drop throbbing phenomenon. It is the evaporation of the surfactant. Now, the shear forces which act all across the surface now selectively pull the surfactant molecules towards the outer surface, rather push these molecules towards the outer surface. Now the equilibrium membrane of the water, omitting the oil drop over here, remains like this just before or just at the instant when the water has completely expanded to its maximum area. Now at that particular instant, what happens is the surfactant molecules at the surface evaporate. Alright. This leads to decrease in concentration of the surfactant molecule. The surface tension at the surface increases, which pulls the surface to its original configuration, that is much smaller than this, the original configuration. Now at a transition state, we will have a situation, quite a weird situation, where these irregular oscillatory surface will be observed, and through derivations it was proven that the pressure variations or the pressure gradient traces the contours. All right, when the pressure variation is plotted across linearly, it traces these contours. Now, as the oil drop is in contact with this surface, these forces will definitely act upon the oil drop. Now, we have seen the forces which cause the expansion. Here, these forces will tend to reduce the width and thereby increasing the height. Why did I call this phenomena as the most important process in the oil drop phenomena? Well, the reason lies in the lid coverage. What the researchers did was they covered the surface with a lid, alright, thereby stopping the air to come in direct contact with the surfactant molecules. What this did was it ceased the process of evaporation, and surprisingly, they observed that almost immediately the oil drop throbbing ceases. Alright, there's a damping in oil drop throbbing. Well, this led to revelatory conclusions, alright, and then finally they came to a conclusion that this process is quite effectively the most important process that causes the contraction, right, and then thereby maintaining the entire setup. After I've confused you with a lot of random ramblings and a few practical or technical terms, let us just track down what exactly is happening in this process. Well, first we consider the three interface: the oil surfactant, the oil water, and the air and surfactant. Right? These three interfaces react simultaneously or through a rhythmic process to cause this entire phenomena. What happens is the surfactant molecules within the oil drop tend to go towards the water surface. Those, that is the hydrophilic portion, tries to get towards the water surface, thereby reducing the surface tension at the surface. Now what this causes is this causes the expansion. Now an oil drop is not a uniform contour, or it is not a uniform surface. It has varying thickness all through. Right? Due to this, we have different concentration of oil and surfactant throughout the surface. This causes a different surface tension to be present along all the surface. This causes the phenomena of circulation, and this leads to the force of shear, that is the shear force which is acting. Now this shear force interestingly selectively pushes the surfactant molecules outwards. Now as the surfactant molecules are at the outer layer of the oil drop, like over here, they come in contact with the atmosphere or the air, and thereby they are evaporated. Their concentration decreases, the surface tension of the surface increases, and hence we have the contraction. Now this contraction resets the setup to the original state, right? Surprisingly. And then this process is repeated rhythmically until we have the surfactant molecule to support the evaporation process. Once the surfactant molecules run out, the oil drop reaches its equilibrium position and thereby no longer exudes the rhythmic contraction and relaxation. Right? Now that we have been loaded with theory, let us get down to actually what is happening in this process. Let us get a hands-on on what is exactly happening.
So first of all, we pour some clear water onto the plate, right? We add a few dabs of hot water, not too much. This is just to clear out, or just to clear out any ripples that might be there in the water, and also to increase the temperature of water so that the phenomena can be a little prominent, so that it can be seen on the camera. Then we dip the spoon into the soap solution, and then take the uh, oil solution that we have and carefully making a drop, I pour it onto the surface of water. Now you can see that the oil has started to separate. There's no need, I mean, that's a natural phenomenon which happens in emulsification. But if you look carefully at the oil drops, I'm kind of zooming in onto that, we can observe a very prominent throbbing effect. The diameter increases and then suddenly decreases. I'm not sure if you can pick that up over the camera, but I can clearly see the diameter increasing right now. Now, suddenly, as the shape changes, there was a bulging out and the diameter has reduced. This heartbeat like characteristic continues for as long as over 30 to 40 minutes. I will show you in another video that I had taken. I had prepared those oil droplets over 45 minutes ago, and I could still observe the oil drop throbbing property. As you can see, as the diameter keeps changing, it keeps changing its shape. The water surface is free of any visible ripples. The shape changing is quite prominent.
Thanks for watching. As I'm on a learning curve, any comments or suggestions will be heartily welcome and would definitely improve the quality of the future videos. Thank you for watching.